let's do a physics problem. And I'm going to do everything about this problem. Let me explain the problem. So we have a cylinder of water filled to the very, very, very top. And then we have 3 holes on the side of the cylinder. So water shoots out. So the question is, for which hole does the water shoot out the farthest distance? That's the question. Now there's a bunch of parts to this. I'm going to derive everything and make a VPython model. So we're going to have a great time. I'm going to have fun. My cable's a little tied up right there. Okay, there we go. Okay, so let me just answer the question first. And then I'll show you where we get these different pieces from, because we're going to have to take some stuff just on faith. Not completely, but mostly. So first of all, I'm going to say that let's look at one of these holes. It's a distance y from the bottom and a distance h underwater. And then these are all separated by the same distance. So these are, I'm going to call all these s, 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 s. And you can pick whatever values you want for that later. So the first thing is that when the water comes out right here of this one, it has some initial velocity v0 in the x direction. And how fast is that? Well, it turns out that we can treat this as though the ball started, a little ball of water started up here, fell down here, and then shot out. And I'm going to prove that for you, don't worry. So with that, I could say work is the change in kinetic energy plus a change in gravitational potential energy. The change in gravitational potential energy is going to be negative mgh, right, because it dropped that much. And the change in kinetic energy is going to be 1/2 mv0 squared. And there's no work done. So 0 is 1/2 mv0 squared minus 0 minus mgh. So I get 1/2 mv0 squared is mgh. The mass cancels, which makes sense because it's not really a mass of water anyway, it's just a stream. So v0 is going to be the square root of 2gh. So that's my initial launch velocity. So that's what makes this a good question, right? The further down I go, the faster the water comes out, but it's going to have to drop a less distance in order to go horizontally. But that's my first part. For the second part, we have projectile motion. So now I'm just going to take this. I have, it starts at a position y, it starts with the initial velocity v0, and I want to find out how far it goes x. So for projectile motion, we can treat the x motion and the y motion separately. So in the x motion, I have x final is x initial plus vx initial, it's called v0, times t. And so if I knew the time, I know my initial x0 is 0. I'm going to say it's 0. I'm trying to find that. So I just need my initial, I have my initial velocity. It's right there. I just need my time. So in the y motion, I can use the kinematic equation y0 plus, I'll write it, vy0t minus 1/2 gt squared. Right, that's the kinematic equation, which is the same as that. It's just that there's no acceleration in the x direction. Now here I'm starting with an initial, I called it y. Okay, so that's 0. The final y position is 0. So 0 is y, and the initial y velocity, it's shot horizontally, so that's 0 minus 1/2 gt squared. So y is 1/2 gt squared. T is the square root of 2y over g. That's all in the square root. Okay? Now I can put those two things together. Let me erase this. I guess I can put it over here. So I can say x is v0t. Well, v0 is that, square root of 2gh times the square root of 2y over g. Okay, look what happens right there. The g's cancel, which is kind of interesting. It says if you take this cylinder and you put it on another planet, it's going to shoot the same distance. That's kind of cool. Okay, so those g's cancel. The 2's combined together. I get 2 squared is 4. Square root of 4 is 2. 2 times the square root of hy. And you'll notice the units do work out because meters times meters, square root is meters, still meters times 2, so I get meters. I get distance, so the whole thing works. Okay, now we can just calculate how far each of these go. So here, let's just do it. We'll call this 1, 2, 3. x1 is going to be 2 times the square root of its height, which is going to be s, times, I'm sorry, h is 3s. 3s times its height, s. So I get 2s square root of 3. And then x2, I have h and y are both 2s. So I get 2 times the square root of 2s times 2s equals 4s, right? Yeah. And then x3, I have the same thing up here, because now h is s and y is 3s. So I get 2 times the square root of s 3s equals 2s square root of 3. So that's kind of cool, right? These two go the same distance, and that one goes the farthest. Now, if you don't have them evenly spaced or you pick different spacings, then the answer is different. But there you go. It's a good problem. But we're not done. I told you I was going to show you this, right? That's a trick, and we don't have to use that trick. Instead, we can use the pressure as a function of water and use that, which I'll derive also, and use that to find that velocity. So I'm going to do that, and then we'll do a Python model, and then we'll be done. Okay. So I'm going to show this thing right there, which I'll put over here. I can erase all my data right there. V0, I didn't even need to erase that. V0 is the square root of 2gh. That's what I want to show. Okay. So erase this stuff. The first thing I want to show is that if I have some water and I'm down here, the pressure, and this is a height of h underwater, the pressure is rho gh. So rho is the density of water, g is the gravitational field, and h is that value. So how do we get that? Okay, so let me erase this and start over, because I don't want to draw the cylinder. It makes me feel uncomfortable. Suppose I have a little box that's this long, and it has an area of s by s. It's s squared, and s is just my little length of that box. I can draw the whole thing. And it has a height of h. That's a column of water in water, and I know that that column of water stays there. If that column of water stays there, then I know there's a gravitational force pulling down on it, mg, and then there has to be some force pushing up on it from F, I'll call it the pressure of the water. Now, in this calculation, I'm going to assume that the air pressure on top is 0, and that's an okay assumption. So let's calculate the mass of this water right here. Well, the mass is going to be the density of water times the volume, which is going to be the density times the volume times s squared. Okay. And so the gravitational force is m times g times that. And that has to be equal to the upwards pushing force. Now, that's going to be due to the pressure down here. So I can say the force of the pressure is the pressure times the area, which is pressure s squared. Right, because it's the size of that box pushing up on it. Now, I just want to say that's equal to mg, so I get p s squared is the force pushing up, and that's equal to the mass rho v s squared g. Where's my h? Oh, this is, what did I do? h. So now if I solve that for pressure, I get pressure, the s squareds cancel, and I get rho gh. So the pressure does increase with depth. It has to in order to support the water above it. The deeper you go, the more water it has to support so it stays there. Okay, so that's that. Let's put it over here. Pressure, rho gh. Now let's go back to our container of water. So here's the water, and then here's the wall. So that doesn't look over there. And then here's a hole. And this hole has a size, an area of A. And so I know that this is a depth h. I know that there's pressure pushing on that hole. P is rho gh. So that means that if I take a little piece of water right there, there's going to be a force pushing it. F is rho times A. I mean P times A. That's the force pushing on it. Now suppose that that water moves a distance dx, a tiny distance dx. It gets pushed a tiny little distance, and that force is pushing it as it leaves. So I can say the work done on that water is going to be F times dx. And that's going to be the change in kinetic energy. So that's going to be 1/2 mv squared minus 0, because I'm going to say it started from rest. Well, what's the mass of that little tiny piece of water over that distance? Well, the mass is going to be A dx times the density of water, rho. Right? So the mass, the volume times the density. So let's put in the pressure, the force, and everything. So the force is P times A. So it's P times A equals dx. That's the work done. And that's 1/2 mass A dx rho v squared. Now I want to put in the pressure, rho g h A dx 1/2 A dx rho v squared. I know that looks like a lot, but it's not that bad, because look, rho cancels, dx cancels, A cancels. So I get gh equals 1/2 v squared. Now if I multiply both sides by the mass again, I get back to where I wanted. But I don't even have to do that. I can just solve for v. Okay. So I told you I would do that, right? So now we can use work energy to find the velocity of water coming out, and then use projectile motion to find how far it goes. Now we're going to make a Python model, because the Python model is really nice because we can visualize the whole thing, and that makes it fun. Let's just get to it. Okay, jumping over to web VPython. So the first thing I'm going to do is to make a cylinder. Well, let's say I need g equals vector 0, negative 9.80. Going to need that, right, to model this. Make this bigger. What else do I need? I need s. So I need the size of each step. Let's say s is 0.05 meters. I just picked that. I don't really care. Okay, so now let's make our water tank, our cylinder. So I'll say tank equals cylinder. Position is vector 0, 0, 0. So in web VPython, a cylinder has a location on one end, and then an axis tells you the vector from that end to the other end. And I put an extra comma there. Okay. So that's, I'm going to start it at the ground, and then I need to go up. So the axis is going to, it's going to be 4s long. So the axis is vector 0, 4 times s, 0. Now I also need the radius. Let's say the radius is just s for now. Let's see what that looks like. Let's give it a color. Color equals color dot size. He's going to use blue, but it doesn't look that great. And then let's make it partially clear. Opacity equals 0.5. And then let's run that, and let's just see what it looks like. Okay, there's my column of water. Isn't that nice? Okay. Next, let's go ahead and give it a floor too. And there's going to be a box. I'm going to actually put it in the wrong spot. Let's say it has a position. Oof. Should I put it off? I'm just going to put it in the middle. Position. When you start drawing these things and trying to make it look right, you're going to have to kind of like fudge all the numbers a little bit. The problem with a box is that the box, the position is the center of the box, but then you need to shift it up and down according to that. So I'm just going to pick position equals vector 0x, and let's say 0, negative 0.05. I'm having trouble typing 0. And then the size vector is going to be equal to, let's say, 6s. 6 times s in the x direction. 0.1, and then 3 times s. And then I'll leave the color blank. So it'll be there. Oh, that's really thick. Okay, I don't need it that thick. Let's change this to 0 and 0. Okay, that looks pretty good. I might need to make it wider in order that my water hits the thing. Okay, now for my water, I'm just going to use a sphere. So my sphere is just going to be a water that leaves a object that leaves a trail. And I guess I could make it cyan, but I'll make it a little bit less opaque. So let's call this ball 1. It's a sphere, and then I'm going to put it at the bottom. So its position is going to be equal to vector. Now, I don't want to start at 0 because that's in the middle of the tank. I want to start at the edge of the tank, which has a radius of s. So it's s 0. And then let's do this. h1 equals 3 times s, y1 equals s. So I'm going to use that in my calculations, right? That's the initial y position is h. The depth of the water is 3s. So down here, I can just say y1. Okay. The radius is going to be equal to, how big should I make this? I'm not really sure. Let's say 0.005. Color equals color.cyan. Make trail equals true. Okay, let's just run that, see what it looks like. Okay, that looks good. A little thick, but that's fine. Now, in order to model the motion of this, I'm going to need its initial velocity. So let's calculate its initial velocity, b1.v. I'm going to give it as a property of the object. And now I'm just going to use that equation right there, 2gh. And I already have h. So it's going to be vector square root of 2 times g mag g, right? I can't take the square root of a vector, mag g times h1. That's its it's in the x direction, and the y direction, the z direction is 0. Yeah. So the mag takes the magnitude of the vector g, which is what I want. I use the scalar version of g. Now I got the position, I got the velocity. Let's just model it. Okay. So t equals 0, dt equals 0.001. I'm going to do it like that. And let's say while b1.pos.y is greater than or equal to 0, right? So until it hits the ground. Rate is 1,000, so then it'll run in real time. It doesn't really matter, I really want the picture. So the first thing I'm going to do is update the velocity. I don't need to calculate the force, I don't need to calculate the mass, because I don't really care, right? I know the acceleration is negative 9.8. So ball1.v is ball1.v plus g times dt. And remember, g has a negative y component, so I'm not going to put negative g. It's just plus. G is a vector. Now I can update the position, b1.pos, b1.pos plus b1.v times dt, and then update time, t equals t plus dt, which you don't actually have to do. And let's run this and see if it works. There you go. So there's my water that shot out, and like I said, my floor is not long enough, so let's make that longer. 6s, let's try 9. I don't know. Okay, I'm going to need to make that longer because I know that that one doesn't go the longest, so let's say 12. Now, a couple of other things. If you move the whole stuff down, it'll automatically zoom into more of the space. You can move it in the lower left-hand corner, but I'm okay with this. If I wanted to make this really nice, I might do that, but I don't really care. That's good. Now let's do the next hole. So I can just copy all of this. I'm going to copy that and paste it. And then I'm going to change this to 2, and 2 has a depth of 2s and a height of 2s, and this is 2, and this is 2, and then I change this to 2. You see how this is nice? I don't have to change that stuff. That's 2, and that's 2. And down here, okay, now I'm going to have to do something. We'll do it in a little bit. I can just copy this and do the same thing for 2. Just go boop, 2, 2, 2, 2, 2. Okay, now let's run it. It's not going to be perfect, but it's, and I didn't need to save it. Okay, run it. And you'll notice that it hasn't had enough time for that ball to get to the ground because it started at a higher point. So what I want to do is to run it until ball 2 gets to the ground, but if I did that, this one would be below the water level, the ground. So I can fix that. Let's just do this. While B2 is greater than or equal to 0. And then right here when I update the position, I'm just going to say if b1.pos.y is less than 0, then b1.pos.y equals 0. So it just won't keep going down. It's still speeding up. It just won't go down. There you go. Oh, it kept moving. It kept moving horizontally. They both did. Oh, that's weird. Okay. Let's just say b1 dot. Let's say and b1 dot v equals vector 0, 0, 0. Try that. There. Okay, nice. Now we're going to need to make our last ball of water. Copy all this, paste it, and we're going to change these to 3. So in this case, it's 1s deep and 3s above. And then that's a 3, 3, 3, 3, and 3. And then down here, I just need this again. Copy, paste, 3, 3. You have to say it when you change it. If you don't say it, it won't work. It'll give you an error. I'm just kidding. Okay, run that, and we're going to have to make another condition. Okay, so it didn't get down to the ground yet. So let's go up here and put the same condition for B2. Oops. If, this goes right here. If B2.pos dot, and then 2, 2. And then let's do this as while B3. And I think we'll be done. Okay, look, I told you those two would hit the same spot. They did. One thing we could do is, I'm not going to, because it's already long, and I'm pretty happy with this. One thing you could do is to print out the final position of that and calculate its theoretical position, show that you get the right thing. But there you go, look at that. Now the next thing is to build this in real life, which I was going to do, but I didn't do because I was like, I don't know if I want to do that. But I'm pretty happy. It's pretty cool. You can make these different colors if you wanted to also, but that's that. Okay, that was a fun little offshoot from my normal classical mechanics stuff, which I've been doing, but I hope you enjoyed that. Code for this down below. Let me know if you have any questions.